Thank
So,
you.
a very good morning, good afternoon, and good evening to everyone. I would like to formally welcome you to this UXL Foundation's special interest group on AI and scientific computing. This group has basically evolved from a SIG on AI, and now we are also planning to, converge the discussions with scientific computation. Just to give you a quick overview, UXL stands for Unified Accelerator Foundation, and we are like almost 3 year old. This foundation has people from different companies like Intel, ARM, Google, um, Samsung, Qualcomm, Imagination Technologies. So we all work together and work on various reforms and standardization towards contributing to one API ecosystem. And so this is a long story. I would like to focus more on this particular SIG. So the vision of this SIG is basically to work towards the convergence of AI-driven methods and scientific computing workflows that is enabling innovation across simulations, AI surrogate modeling, and data-driven discovery on modern computing platforms. And we conceptualize this forum for bringing discussions at the convergence of AI and scientific computing together. My name is Priyanka. I work with Fujitsu Research. From this day, I have joined as the chair of this joint SIG on AI and scientific computing. Originally, the session was led by Penporn from Google and Lee from Intel. And then we will also be joined by Ragesh from my team. He also works with Fujitsu. So next, I would like to invite Penporn to share some of her insights on this SIG.
Thank you very much for the introduction, Priyanka. And hello, everyone. Welcome to existing AI SIG members and also the new joiners. So the AI SIG in the past few years, we have focused on mostly AI topics and discussions of related UXL components such as 1DNN and 1DAO. But and also its integrations with frameworks such as PyTorch and TensorFlow. But even though we didn't mean to limit the scope of the AI SIG to just mostly purely AI applications, we found that in the past few years, over a dozen talks that we have, so it's mostly just focused on 1DNN or 1DAO, or the application talks are mostly just about large language models, even though we didn't intend to mean it that way. And then Priyanka and other people, and also us, also heard more from the community that, there are a lot of interest in talking about scientific applications, but there isn't a venue that is fitting for that. And this brings up the interest for the whole scientific computing SIG. But then it's also overlaps a lot with AI, as a lot of scientific computing applications are now using AI in development. So we thought it would be good to just combine the two things, the two SIGs together. The more the merrier. so that become the SIGs. And Jianhui and I both also joined the SIG to kind of like merge our power together and now that we have even more topics to cover, we're thinking of making this SIG meeting happening more often, just increasing from just once a quarter to maybe twice a quarter. And if you notice the new time change, so the old time used to be morning Pacific time, which is evening Europe time zone, which is not convenient for Asia time zone at all. So now we have moved to the new time, and to make it possible for more people to attend. And if you have any feedback on the time, for example, if you wanted to alternate between morning Pacific time and morning Asia time, or pick another time, or if this time is good, please give us the feedback on the time as well. And with that, I'll give the mic back to Priyanka. Thank you.
Thank you, Penporn. Yeah. So okay, so I'll just go with a brief introduction of this SIG. So as Penporn said, this SIG will be led by Google, Fujitsu, and Intel, and will be focusing on driving technical discussions and knowledge sharing on AI frameworks and scientific computing, with UXL software serving as the foundation for scientific frameworks and applications. We'll also be contributing towards acting as a bridge between scientific R&D communities and developers to foster collaboration and innovation. As Penporn said, we would want to host regular meetings online and offline as well. Offline meeting is still under discussion, and we'll try to match up with some of the previous conferences like OSS Summit or Supercomputing India or ISC conference, premier HPC conferences. It's still not decided, and if the offline SIG gets offline venue and time for SIG gets decided, we'll surely share it on our common channel. During the regular meetings, we want to share community proposals, case studies, technical advancements, challenges, and contributions, and also cover feedbacks and requirements to guide UXL component development. We also want to work towards identifying common patterns and requirements in scientific computing and aligning them with AI surrogate model and frameworks. And as Penporn said, we want to have this like twice a quarter, preferably on third and fourth Thursday of alternate months. Timing would be similar to this, and we actually crafted this time to invite participation from our Japanese and Korean collaborators, as well as American or European collaborators and Indian collaborators. So that's why we tried to work on this timing. Please let us know if you have any other suggestions in reference to getting more people onboarded in this SIG. Now, I will go ahead formally in reference to giving you a brief of why we need to work on AI and scientific computing towards expanding AI for science. I work with Fujitsu Research of India as the executive director, and I also lead Monaka Software R&D unit from India side. Monaka is Fujitsu's 2-nanometer ARM chip, and we contribute heavily to OSS-based AI frameworks and data platforms, and that's why I'm very passionate about being a part of this foundation. So I was fortunate to be the founding steering committee, and we worked together, Penporn, Ellison, a lot of us together to bring this foundation to where it is today. The last line in my profile I wanted to share, because I'm also one of the general board member of Indian National Science Academy. So this is a very premier organization in India that works to bring scientific community together. Now, I'll just take a few more minutes and give you a quick vision of this SIG and the scientific computing alignment with UXL. What essentially are we looking for in this particular SIG, right? How does it connect with UXL? So I wanted to give you some examples in that reference. And then I will invite today's expert speaker, Professor Tsubokura-san. He's a professor with Kobe University, and he works very closely with Japan's RIKEN lab. So this slide that you see basically shows the scientific computing workloads aligned, how scientific computing workload is aligned with UXL software's ecosystem. At the top, we see domains like CFD, molecular dynamics, genomics, climate, and engineering. And today's talk is going to be focused on, today's talk by Professor Tsubokura is going to be focused on computational fluid dynamics. Then on the lower part, if you see, this is a typical scientific ML workflow that spans across 4 stages, which includes data pre-processing that I'm sure everyone who has connected knows. The second part is surrogate training. So by surrogate training, what we mean is AI models, they basically learn complex physical behaviors from simulation data to approximate expensive numerical solvers, right? And The next stage, which is important here, is scientific AI inference, which typically means that these trained surrogate models enables fast real-time prediction of scientific outcomes by replacing the costly HPC-based simulations, right? And that's why they are important in today's world. And then, of course, this pipeline has validation, deployment, and scaling, where models are validated against ground truth and they are deployed at scale for large simulations and production workflows. On the lower bottom, you can see popular scientific and AI frameworks like NumPy, PyTorch, DeepXD, GROMACS, and Dask, which operates at various stages of this pipeline. And UXL basically provides the performance backbone for these workflows and has various library ecosystems like Wandal, which contributes to accelerate pre-processing across classical AI ML pipelines. Then we have OneMath, which provides optimized numerical kernels, for example, BLAS, LAPACK, FFT, and RNGs. And then we have SYCL, which enables portable execution across heterogeneous systems. We have OneDNN, which accelerates AI model training and inference with optimized deep learning kernels. And we have OneTBB, which enables scalable parallel execution. So, and there are many more. So, you can go to OneAPI website and you can get to know about various other specialized stacks that OneAPI offers. Now, in this slide, I wanted to give you an example of how AI surrogate models are used in advanced industrial AI. So, this use case is from CAE Design with AI Surrogate Model. The goal here was to achieve cost-effective, high-accuracy design by enabling rapid evaluation and improved decision-making early in the design cycle. So here, as you see, our approach was to use GNN-based surrogate model, which is built on graph representation of simulation data, thereby enabling better generalization across different shapes and conditions. And the workflow has of this simulation has graph construction, training, fast inferencing, and the result that you see on the right hand side basically shows strong agreement with OpenFOB simulation, thereby demonstrating both accuracy and adaptability across different geometrics. So from a system perspective, UXL software stack can play a great role in what has been achieved here, and that lies in the way we have used Wandal and OneMath for pre-processing and the numerical kernel optimization, and OneDNN for accelerating AI inference. Now with this, I'll go to the next slide. So here you can just see a quick walkthrough of some of the result, because that also helps you understand the goodness of working with this ecosystem together. So you can see that typically AI surrogate model can help us accelerate HPC simulations by almost 25x, which is a very big gain, right? And the middle diagram that you see basically shows basically shows the kernel level optimizations where we can use OneDNN and PyTorch scatter gather kernel. So some of these things which I spoke previously, I will not discuss much on this because Professor Tsubokura has a wider and interesting content to be shared with the audience today. But the purpose of this graph was basically to show that how AI surrogate model can give us higher accuracy and higher speed up as well. Now, this is some of the resources which you can capture. This will let you know more about the Unified Accelerator Foundation, then AI and Scientific Computing SIG, and you can subscribe to our mailing list, and get regular updates. You can also, it can be a two-way communication where you can share the updates as well. And the presentation of our SIGs are going to be placed at this particular link from that's GitHub repository of UXL Foundation. Now, I would like to invite and introduce you all to Professor Tsubokura-san. He's the guest speaker of today's session, where he'll be talking about how AI meets engineering design. Professor Tsubokura works as a professor with the Graduate School of System Informatics at Kobe University, and he's also the team leader at RIKEN Center for Computational Science, Japan. He specializes in computational fluid dynamics, HPC, and applied aerodynamics with a focus on development of numerical methods for turbulent flow simulations on massively parallel architectures. He has also authored more than 100 peer-reviewed research papers, 30 plus review articles, and delivered more than 50 premier plenary and invited talks at international conferences. He is the fellow of GSME, GSFM, GSAE, and a member of Engineering Academy of Japan since 2020. Some of his honors include the Software Japan Award, Japan Open Innovation Award, Minister of Education's Commendation for Science and Technology, then 2023 Computational Mechanics Award. In 2021, he received ACM Gordon Bell Special Prize for COVID-19 research using supercomputer Fugaku. Since 2023, he is serving as an associate member of Science Council of Japan. Our team in Japan is fortunate to be working with Professor Tsubokura-san. Professor Tsubokura-san, a very warm welcome to you. And now the floor is all yours. Thank you for accepting our invitation.
Okay, thank you very much for the introductions. First, I'd like to share my slides, but I think yeah. Okay, want to
Now
check?
you can share, yeah.
Okay. Okay, let's start. Good morning, everyone. Or maybe someone, it's maybe a good evening. Anyway, first of all, I would like to sincerely thank the organizers for giving me this opportunity to speak at this meeting. I'm Makoto Tsubokura from the Kobe University and RIKEN. It is a great pleasure for me to have the opportunity to share our recent work with you today. Before going into the main topic, let me briefly show you what our group is trying to do more broadly. Our group develops AI-ready CAE technologies for real-world engineering. In other words, we are interested in connecting the physical space where products are actually designed, manufactured, and operated with the cyberspace where high-fidelity simulation, data analysis, and optimization can be performed. On the right-hand side, this idea leads to what is often called a digital twin. If we bring real-world driving data and environmental data into cyberspace, we can reproduce complex aerodynamic simulations and eventually support better vehicle operation and performance assessment. On the left-hand side, the same framework leads to digital optimization. Here, instead of analyzing an existing product, we try to generate better candidate designs automatically by combining high-fidelity simulation, AI, and multi-objective optimization. In vehicle design, this is particularly important because engineers and stylists often have different objectives. Engineers care about aerodynamic performance, stability, and efficiency, fuel efficiency, while stylists care about proportion, identity of the shape, and market appeal. So the question is, can AI help us explore designs that satisfy both of them? Today, I will focus on this left-hand side, namely digital optimization for aerodynamic vehicle design, and discuss how AI can become useful only when its creativity is properly constrained. To make AI useful in engineering design, we first need a simulation framework that can generate training data fast and enough. AI requires many simulations over many different shapes. And in conventional CFD, the bottleneck of the simulation is often pre-processing, especially for the engineering applications. And also it includes some mesh generations from a dirty CAD data shown here. That is why we developed our own CFD software that is called Cube. It uses a hierarchically structured mesh and immersed boundary method, which allow us to avoid expensive body-fitted mesh generations. As a result, pre-processing, including mesh generations, becomes about 100 times to 1,000 times faster for the simulation of real vehicle shape on one of the world's largest supercomputer, Fugaku. This gives us a much better turnaround time for large-scale data generation, which is essential for AI-assisted design. So before talking about AI models themselves, I would like to emphasize that the simulation infrastructure is the real enabler. In short, if AI needs data, then simulation turnaround time becomes a first-class design issue. Cube, our software named Cube, showed its strengths in a way we had not originally expected. We had developed it for engineering applications, including spray simulation for internal combustion engines. But when COVID-19 emerged in 2020, we quickly realized that the same framework could be adapted to a droplet and aerosol dispersion shown here. So when the Fugaku resources were opened to a COVID-related research determined by Japanese government, we proposed aerosol simulation based on the technology we already had. This was a very rapid pivot from engineering CFD to a societally urgent application, and it clearly showed the flexibility and responsiveness of our simulation framework. After the rapid pivot I mentioned, the next challenge was scale. During the pandemic, what we needed was not just accuracy of the simulation, but also speed of the simulation, and also the responsiveness and the ability to evaluate many real-world simulations, also remotely. Using Fugaku and Cube, we assessed more than 1,500 cases across over 70 realistic scenarios over 2 years. So this slide demonstrates three important capabilities of our framework. It was remote, it was massive, and it was responsive. And these same capabilities are also essential for AI-driven engineering, where we need to explore many cases in a short time. In other words, this was not just a scientific study. It was a demonstration of a simulation infrastructure that could respond to society in real time. This slide shows the societal impact of the work. The simulation helped people understand aerosol risk visually and intuitively, which improved public awareness of measures such as masks and ventilations. They also supported policy decisions of the government and guideline development by providing scientific evidence for decision making. Our work was therefore covered very widely in newspapers, televisions, and web media. And for us, this was an important lesson. Simulation becomes much more powerful when it is not only accurate, but also timely, scalable, and understandable. And this is also the mindset behind our work on AI-assisted engineering. Simulation should not remain an isolated analysis tool, but become an active partner in decision-making and design. Now, let me turn to the main topic of today's talk. Our group is working on the fusion of HPC simulations and AI for engineering designs. There are many possible directions in this framework, but today I will focus on only three. The first is the surrogate modeling to predict aerodynamic performance quickly from shape data. The second is multi-objective optimization to balance competing design requirements. And the third is a generative or inverse design, where AI starts to suggest shape modifications rather than just evaluating existing ones. Together, these are three elements from the core of our approach to AI-assisted aerodynamic vehicle design. Okay, let me begin with a simple question. Why AI for product design in industry so difficult? There are two main reasons. First, industry products are, of course, complex and three-dimensional. So each data point is much larger and more structured than in the typical image-based AI tasks. Second, reliable training data are very expensive. If we want accurate aerodynamic, we would like to obtain the accurate aerodynamic levels, we need high-fidelity CFD, and that makes data generation very costly. So in this program, we have the worst combination: high dimensionality and limited data. That is why too much freedom hurts learning. If we allow AI to explore shape variation freely, the learning problem quickly becomes insufficient and impractical, actually. So dimensionality reduction is not optional here. It is essential. And in the following slides, I will show three ways we use parametric geometry, PCA, and latent space editing. So first task was to find compact representations of a complicated vehicle shape. Here, we used a morphing-based parameterization method, where a reference geometry is smoothly deformed using a limited number of parameters. In this way, complex three-dimensional shape variation can be expressed in a much lower dimensional form. In our study, we used 29 morphing parameters. A very important point is that these morphing points were selected together with engineers and stylists at Mazda Motor Company. So this is not just a mathematical compression of shape. It is a design representation that already reflects practical engineering and styling knowledge. And these compact representations become the basis of the AI models that I will show next. In other words, before asking AI to learn shape, we first define a language of shape that is compact, controllable, and meaningful to designers, for both engineers and stylists. Once we had the 29 parameter shape representations, we used it to build a surrogate model for aerodynamic performance. We generated 232 shapes by varying the 29 parameters, and for each shape, we ran HPC CFD to obtain drag and lift coefficient that is essential for vehicle aerodynamic performance. Then we trained a neural network to predict these aerodynamic quantities directly from the shape parameters of 29 for each vehicle. Even with that, only the 232 training samples, this is actually a very, very small value. The model achieved about 2% prediction error for the drag coefficient. That means it can work as a practical surrogate models to predict drag coefficient from the shape. So instead of evaluating every new candidate with expensive CFD, we can first use AI for a fast prediction and use CFD much more selectively. This surrogate model is not the final goal by itself, of course, but it becomes a key accelerator for the optimization framework that comes next. The point of optimization is that vehicle design is inherently a multi-objective problem. We care not only drag, but also about lift, stability, and other performance measures. These objectives often conflict with each other, so there is usually no single-best design. Instead, we need a set of balanced solutions that represent different trade-offs. That is why we use a multi-objective evolutionary algorithm called cheetah-R. It is particularly suitable for nonlinear aerodynamic design problems, and it was developed JAXA in Japan. The goal is to obtain a parade front where each solution reflects a different compromise among the competing requirements. So at this stage, AI is no longer just predicting performance. It starts to support decision-making in design space exploration. This slide shows how the optimization loop actually works. First, optimizer proposes a new set of shape parameters. Then the morphing tool converts them into a vehicle shape shown here. Next, we evaluate the aerodynamic performance of that geometry. For this step, we use a hybrid strategy. One is a surrogate predictions when possible, and the other is a high-fidelity CFD when needed. The resulting objective values are fed back to the optimizer, which then generates the new generation candidates. So in essence, this is a closed loop connecting parameterized geometry, AI-based predictions, CFD, and multi-objective optimization. That integration is what makes practical design exploration possible. So rather than replacing CFD with AI, our goal is to orchestrate both in a single efficient design loop, as shown here. Okay, this slide shows the results of unconstrained optimizations. We optimize 3 objectives here, including drag, lift, and yaw-related drag variations. And after 50 generations, we obtain a clear parade front, you see here. So technically speaking, the optimization really worked. But when we look at the generated shapes, a serious problem becomes obvious. Many of them were aerodynamically good, it is no doubt, but are visually unbalanced and unrealistic, as shown here. So the optimizer did find better solutions, but not the kind of better solutions that a real design requires. This is why physical alone is not enough. We need constraints beyond physics. And this was the moment when we understood that engineering design is not only about performance optimization, but also about controlling the freedom of shape variation. These results lead to a more fundamental question. In engineering, we often hear the phrase "form follows function," but in vehicle design, that is only partly true. Cars are not evaluated only by its performance, aerodynamic performance. They are also judged by styling, identity, and market appeal. So even if AI finds a shape with better aerodynamic performance, that does not mean it is a good product design. That is exactly why unconstrained optimization failed in the previous slides. Performance alone is not enough. So the real question is not how to optimize shape freely, but how to guide shape variation in a way that remains meaningful to both engineers and stylists. Okay, then why do engineers and stylists so often conflict in design? Because they see the same shape differently. Engineers tend to focus on local surface change and their effect on aerodynamic performance. Stylists, on the other hand, tend to focus on overall proportions, balance, and visual identity. So their objective functions are different from the beginning. This is why AI cannot rely only on engineering metric. If it does, it may improve performance while just destroying design coherence. So the real task is to make AI a bridge between these two viewpoints. And once we understand this, the next question becomes clear. How can we learn the stylist-approved regions of the design space instead of letting AI search freely? Our answer was to learn that regions, restricted region directly from a real vehicle already on the market. Instead of defining styling constraints by hand, we collected about 170 commercial SUV shapes sold all around the world. These shapes are important because they are not arbitrary. They are production vehicles already approved by professional stylists and accepted in the market. So this dataset gives us a practical data-driven notion of what a realistic vehicle shape looks like. And the next step was to express these real vehicles inside our own 29-parameter design space. To do that, for each commercial commercial SUV vehicle, we fitted its shape into our 29-parameter design shape. Starting from the base SUV shown here, we tuned the 29 morphing parameters I showed before so that the morphed shape matched the target vehicles as close as possible. As a result, each real production vehicle of 170 could be represented as one 29-dimensional vector. This is important because it means that a real market-approved vehicle can now be described in exactly the same shape language that we use for optimization. So from here on, reals can be handled directly inside our design space. And that naturally leads to the next step, applying PCA to identify the dominant modes of a realistic shape variation. What we obtain from this PCA, so-called principal component analysis, shown here, as a PC1, PC2, and so on. Each of these is a 29-dimensional vector that represents a typical pattern of shape variations observed in real production vehicles obtained from 190. A new shape can then be expressed as the average shape plus weighted combinations of these components. Here, the weighted coefficient are what we call the score. So instead of using a completely free 29-dimensional vector as a design variable, now we use these scores over 12 as the new design variables. In this way, the search space is no longer arbitrary now. It is restricted to a combinations of realistic shape variations learned from the market. In our case, the first 12 components explain more than 80% of the total variance. That is why we use only 12 scores for the design for the optimizations. So PCA helps us not only reduce dimensionality but also constrain the design explorations in a realist-aware way. Using these PCA-based representations, we've performed the same multi-objective optimization again. The difference is that this time, we did not use the original free 29-dimensional design variables. Instead, we used the PCA scores as the new design variables. So the optimizer could move only within the realist area space around from the real market vehicles, and the result is clear. We still obtain aerodynamically improved solutions, but now the generated shapes remain much more realistic and stylistically balanced as shown here. And this is a closer view. Above is a stylistically not balanced. I previously shown you. Here, this is a new vehicles. It is optimized with style maintained. So the important message is that the constraint did not weaken the design search. It improved by guiding the optimizer toward meaningful solutions. Constraints do not necessarily reduce creativity. In engineering design, the right constraints guide AI toward meaningful solutions. Up to this point, I have focused on shape optimizations as a search problem. But in real product development, designers often face different questions. They do not ask for a completely new optimal shape. Instead, they ask for improvements to an existing shape while keeping its overall character. For example, they may need lower drag without changing the appearance too much, or better fuel efficiency, or by reducing the drag without sacrificing cabin space itself. So this becomes an inverse design problem. The question is not simply how to search the whole design space, but how to modify a given shape in a controlled way under practical constraints. This leads us to the next step, where AI begins to act as a design partner rather than just a predictor or optimizer. So the new question is, can AI tell us not only which shapes are good, but also how to modify a given shape toward a desired target, while preserving its identity? To address this inverse design problem, we move from explicit parameter optimization to latent space editing. The basic idea is as follows. First, we represent each three-dimensional vehicle shape as a signed distance field, or SDF, on a fixed grid. This gives us a volumetric representation of the shape. Then, using an encoder, we compress the shape into a 128-dimensional latent vector in this case. So instead of modifying the geometry directly in physical space, we work in this compact latent space. The key point is that during training, the model learns directions in latent space that reduce drag. In other words, for a given shape, AI tries to learn how to move the latent representation towards better aerodynamic performance. But at the same time, we do not want the original design identity to collapse. So the loss function also includes a term that that includes a term here, which keeps the edited space close to the original one. This is an important idea. The goal is not to generate an arbitrary low drag shape, but to edit a given shape in a controlled way while preserving its character. So in this framework, AI is not just predicting performance or searching globally. It is learning how to modify shape in a directed and interpretable manner. So the question becomes not which shape is best, but how should this shape move in latent space to become better without losing itself. For this study, we used Drive AirNet++ as the training and evaluation dataset. It contains 300 vehicle shapes with simulated drag values and the shape derived from 3 base categories shown here, that is estate back, fastback, and notchback. This is important because it gives us a way to test not only performance improvements such as drag reduction, but also shape preservations. So we evaluate the method in 2 ways. First, where the target CD can be reduced, and also how much CD reduction is achieved. And second, whether the edited shape stay within its original vehicle categories. The second point is especially important because our goal is not free generation, but controlled improvement with identity preservation. So the next question is straightforward. Can AI really reduce drag while keeping the vehicle within its original design family? Let's see the results. This slide shows the results of the inverse design experiment. We asked the model to achieve target CD reductions of 0.02 for each models randomly generated. And in many test cases shown here, it successfully generated shapes with lower drag. And its average reductions is more than the values we ordered, which is more than 0.02. The animations on the right shows 2 examples, an estate back and a fastback. What we can see is that the AI does not change the overall category of the vehicles. Instead, it mainly modifies the lower front and the lower rear, regions of the body. So the model improves the drag in a controlled way while preserving the global design character. At the same time, this method still has room for improvement, actually. Because the editing is performed in the 128-dimensional latent space I mentioned. The resulting geometry shown here is still considerably simplified compared with the real original vehicle shape. We are currently working on this issue, and we are now beginning to achieve similar global shape modification while preserving much more of the original geometric detail. But I will leave that story for the next opportunity. To conclude, the main message of this talk is very simple. In engineering design, the success of AI depends not on unlimited freedom, but on well-designed constraints. A real product design is always a balance among performance, manufacturability, styling, and market acceptance. So AI becomes useful only when it is guided within a meaningful and realistic design space. Today, I showed 3 steps in that direction. First, fast prediction through surrogate modeling. Second, trade-off explorations through multi-objective optimizations. And third, controlled shape improvement through inverse design. In this process, AI is not a replacement for human designers. It is a tool for bridging the gap between engineer and also the stylist. And finally, for industrial use, we also need to define what should be shared and what should remain competitive. So I believe that the future of AI-driven design lies not in unconstrained creativity, but in responsible creativity guided by engineering knowledge. Okay, thank you very much for your attention.
Yes, thank you very much, Professor Tsubokura. This was a great session because you covered all the 3 impacts in the talk, right from the way we should do an ideal surrogate modeling to how this can be connected as a multi-objective optimization problem, and then using AI regulation for changing the shapes in a controlled manner. So I think this was like very, very holistic. I mean, you have covered end-to-end this ecosystem. Thanks for giving each one of us visualization of how we can effectively use AI surrogate modeling for advancing scientific computations. Now, Penpon, would you want to add something to this? Or we should go with Q&A? What is your suggestion?
I just have some quick questions, but maybe let's welcome questions from audience. And if we have some more time, I can ask my questions.
Okay, from audience, is there anyone who has questions? You can unmute yourself and you can speak, or maybe you can write on the chat window. Or I think Penpon, you should start with your questions.
Okay,
that will give ideas to others as well.
Yeah,
let's start with your questions.
So the first question is, so this one is not very technical, but so how high would you think the Tesla Cybertruck would score in your stylist model?
You mean Tesla?
Yeah, Tesla Cybertruck, the big Cybertruck.
Yeah. I think that is a very aerodynamically optimized, I think, and impressive. But due to the many restrictions, it is very difficult to run in Japan, as you may know. So usually the product design is very much restricted, not only the styling, but also the regulations and many things. So designers always have to optimize the shape with a very, very strict restriction. That is a very difficult and challenging point of vehicle aerodynamic designs. But anyway, I think there must be a very powerful aerodynamist in Tesla, I think.
Got it. Thank you. That brings me to the next question. While everyone still think about their question, if anyone has question, please feel free to raise your hand or put it in the chat. Yeah. So the next question is, how do you balance the score between performance and style? So you must give some weight to them, right?
That is a very, very good question. That is depending on maybe usually styling is much more important than aerodynamic performance, to be honest. Because even if you design a very, very good performance car with a low drag it means low fuel efficiency, high fuel efficiency. But if the star is bad, then the people does not buy that one. So maybe the weight is regarding the weight between these two. I think styling is maybe 70 to 80%, and the performance is 20%. But the important point to note is that if engineer cannot achieve the required drag coefficient, in that case, much more tax will have to be paid for the user to buy the car. So the reducing the drag or achieving the high fuel efficiency is very, very important to sell the car.
Got it. One last question from me. So how do you write the simulations? Do you write applications in C++ with 1D and N and other UXL frameworks directly, or do you use PyTorch or other higher level frameworks?
Actually, for the simulation, CFD itself, the software is written by the Fortran. It's very, very classic scientific code, Fortran. But for the deep learning, that we use a PyTorch was such a very common framework for the AI. But currently, we are also trying to develop a graph neural network to predict the pressure distributions on the surface of the road vehicle from the high fidelity CFD. In that case, the learning scale is become very big. So we have to use a supercomputer Fugaku for the learning. In that case, we have to free parallelize the AI framework. That was done in the RIKEN RCCS.
And that's using PyTorch geometry, or?
Actually, I'm not sure exactly which framework they are using, but anyways, the framework itself is very, very common. But we parallelize that one, very massively parallelize the frameworks to be executed for the learning to be executed on the supercomputer Fugaku.
Thank you very much. Any questions from the audience? Oh, yes, Priyanka, go ahead.
No, I wanted to invite Xian Li for your comments or questions, Lee. Over to you.
Yeah, I actually have one question. So is compute a bottleneck for you when you do this, like both simulation and also the model to figure out the best car shape? Like how much compute you really need?
There are so many cases, but in the case of developing the surrogate model, as I mentioned, we executed about 250 high fidelity CFD. Actually, each high fidelity CFD is a bit expensive. It costs about maybe $2,000 US dollars for each CFD. And we executed 250 such a CFD to develop the surrogate model. But once we develop the surrogate models, we can execute the optimizations. In that case, that optimization required about 3 to 400 CFD and 3 to 400 by AI. So the cost is about half when we do not use the AI. And after that, generative AIs, that is not that expensive. That is very cheap. Once you develop the AIs, after that, the evaluations or generating the shape is quite cheap.
I see. Thanks. I saw a question from chat. Yeah.
Oh, would you like to read, Jinhui? Now that you're on anyway.
Yeah. What was the total volume of the training data sets? Was the data exclusively synthetic, or did the training data set includes capture the real world data as well? And what was the data dimension in its raw form, and how did it change?
Okay, for the data set, we generated that ones from the high fidelity simulations, and each geometry was each geometry of the vehicles was generated by changing the geometrical parameter. As I mentioned, it's a 29 geometrical parameters, and we randomly changing the 29 parameters, we generate each vehicle shape. And then we conduct the simulations of, as I mentioned, about 200 to 300 to generate the surrogate model. Data set is something like that. We do not look at the flow field itself. We look at only the CD value or CL values for each road vehicle. If we would like to predict the flow field around the vehicles, then we have to we need a much more data set for the training. But we look at the 29 parameters as input of the shape, and output is 2 or 3 values, including drag and lift coefficient. As a result of that, total data set required is less than 1,200 to 300. That is sufficient. Okay.
Okay, I think we are almost, we have touched the time. Ragesh, would you want to thank from your side and give the last message?
Yeah, I think thank you so much, Tsubokura-san, for your session. It was very interactive and very insightful for all of us. So, and thank you everyone for joining. And we'll have the next session in a couple of months. See you all again.